In this video, we're going to look at some examples of assigning formal charges to atoms in a molecule. In our first example, we want to assign formal charges to each atom in the nitrate ion. So there's a simple formula to use to determine the formal charge, and that is you look at the number of valence electrons in the neutral atom, and then you subtract from that all of the lone pair electrons that that atom has in the Lewis structure, and half of the bonding electrons around that atom in the Lewis structure. So let's take a look at an example in the nitrate ion. So let's do nitrogen first. So nitrogen, the formal charge is equal to the number of valence electrons in the neutral atom. So for nitrogen, that's 5. And then I subtract the number of lone pairs, and nitrogen has no lone pairs, and I subtract 1/2 of the bonding electrons. So if I look at the Lewis structure, nitrogen has 2, 4, 6, 8 bonding electrons around it, and I get to count half of those. So that's going to come out to be 4. So 1/2 of 8. And so the formal charge comes out to be 5 minus 4. So the formal charge on nitrogen is +1. All right, now let's look at the oxygens with a single bond. So my single bonded oxygens, the formal charge is equal to the number of valence electrons in the neutral atom. For oxygen, that's 6. I subtract all of the lone pairs. So these are oxygens that have single bonds have 2, 4, 6 lone pair electrons. And then I get half of the bonded electrons. And there's one bond. The oxygen is single bonded, so there are 2 bonded electrons. So the formal charge is going to be 6 minus 6 plus 1/2 of 2 is 7. So 6 minus 7. So the formal charge on these single bonded oxygens is -1. All right, and then if we look at the double bonded oxygen, its formal charge is 6 valence electrons minus, it has 4 lone pair electrons, 1/2 times 4 bonding electrons. And so the formal charge is 6 minus 6, or 0. So the formal charge on that oxygen atom is 0. Now, when I figure these out, I don't actually use the formula. I just kind of count things up. And let me show you what that would look like. So if I was going to determine the formal charge on this oxygen atom, I would say, okay, I count 1 for the bond, 2, 3, 4, 5, 6, 7, because it gets all its lone pairs. So I would say, okay, oxygen has 6 valence electrons. There are 7 around it. So 6 minus 7 is -1. Or if I looked at this guy, I would say, okay, it has 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. Or if I looked at the nitrogen, it has 1, 2, 3, 4. 5 valence minus 4. It's left with a +1. Another thing that you can do to check that you've got the formal charges correct is that when you add up all the formal charges, it has to add up to be the total charge of the species. So I've got -1, +1, -1. That adds up to be -1. And that's the same as the charge on the nitrate ion. All right, let's look at one more example. Okay, we want to assign formal charges to each atom in a carbon dioxide molecule. So we have our Lewis structure here. So both the oxygens are the same. They're both double bonded to the carbon. So the oxygen with a double bond, its formal charge is equal to, oxygen has 6 valence electrons. These oxygens have 1, 2, 3, 4 lone pairs. So minus all the lone pairs. And then 1/2 of the bonding electrons. They each have 4 bonding electrons. So this comes out to be 6 minus 6 is equal to 0. So the formal charge on each of the oxygen atoms is 0. And if I look at carbon, right, it's got 2 double bonds. The formal charge, carbon has 4 valence electrons, minus no lone pairs, and then 1/2. It has 8 bonds, so that's, or 4 bonds, so that's 8 electrons. So 4 minus 4 is equal to 0. The formal charge on carbon is 0. Or if I was just going to count these guys up, I would do very quickly. I'd say, okay, oxygen has 6 valence electrons. It has 1, 2, 3, 4, 5, 6 electrons that it gets to count. Its formal charge is 0. And again, we want to check, make sure the formal charges add up to the total charge. 0 plus 0 plus 0 is 0. Carbon dioxide doesn't have a charge, so the formal charges add up to the correct total charge. All right, and then we'll do one more example on the next slide. Okay, in this case, we want to use formal charges to determine the best resonance structure for the dinitrogen monoxide molecule. So dinitrogen monoxide, that's, oops, it's N2O. All right, and in this case, we weren't given the Lewis structure, so we want to go ahead and draw the Lewis structures. In fact, we're told that there are going to be resonance structures. So nitrogen being the least electronegative will be the central atom. So we'll have one of the nitrogens in the center. And the oxygen around it, we'll count up our electrons. I've got 5 plus 5 plus 6 for 16 electrons. So I've already given out 4 there with the bonds. That's 6, 8, 10, 12, 14, 16. All right, so I've given out all my electrons, and then I look and say, okay, the terminal atoms, the nitrogen on the end and the oxygen on the end both have an octet, but the central nitrogen does not. It only has 4. So I'm going to need to make 2 double bonds. And I can either take a lone pair from the nitrogen and the oxygen. I could take 2 lone pairs, giving a nitrogen-nitrogen triple bond. I could take 2 oxygen lone pairs, giving a nitrogen-oxygen triple bond. So I'm going to have 3 different resonance structures. So let's go ahead and draw these 3 possibilities. So I can do a double bond on each side, kind of a symmetric looking one. I could do that resonance structure, or I could do that resonance structure. And so to determine which one is best, and then we'll do our little arrows that we typically do for our resonance structures. To determine which one is best, I want to assign formal charges to each atom in each of these resonance structures. All right, so I'm just going to use my little counting method rather than writing out the formula. So the central nitrogen in the first resonance structure, it has 1, 2, 3, 4 electrons that it gets to count because it only gets half of the bond electrons. Nitrogen has 5 valence electrons normally, so 5 minus 4, that leaves this nitrogen with a +1 formal charge. If I look at the other 3 resonance structures, in each case there are 4 bonding pairs around the nitrogen, so that nitrogen is going to have a +1 in each one of the resonance structures. And so the difference is going to be the terminal atoms. And so let's look at the nitrogen in the first resonance structure here. So we get to count 1, 2, 3, 4, 5, 6. So 5 valence minus 6. Nitrogen has a -1 in that Lewis structure. If I look at the second one, I get to count 1, 2, 3, 4, 5. 5 minus 5 is 0. And then in our last Lewis structure, we have 1, 2, 3, 4, 5, 6, 7. So 5 minus 7, it's -2. Now we'll do the oxygens. So in that first resonance structure, 1, 2, 3, 4, 5, 6. 6 valence minus 6, that oxygen is 0. In the second one, 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is -1. And then in our last one, 1, 2, 3, 4, 5. 6 minus 5, it ends up being plus 1. So our rules for which resonance structure is the best, first we want the smallest magnitude of formal charges. All right, and when I look at the magnitudes of the formal charges, the one on the bottom, I've got a -2 and then 2 1s, so that guy is no good. It's clearly the worst. And the second thing that I want to look at is that negative charges should be on the most electronegative atoms. All right, so when I compare my other two Lewis structures, in the top one, the negative charge is on the nitrogen, while oxygen is 0. Oxygen is more electronegative than nitrogen, so it makes more sense for the negative charge to be on oxygen the way it is in the middle. So the best resonance structure is that one.